Hello. I'm going to start off with a terrible disappointment, which is I'm not actually Philip Jarvis. I'm a pale substitute. So I'm Richard Atkinson, but I am part of the Coomtech team. So I'll take you through the technology, and I'm happy to answer any questions. So I don't know if any of you come from the materials or construction or process industries, but a lot of the materials that we use and that you see around you have been washed and therefore dried at some point in their journey. So drying materials is kind of a staple of the industrial world that we live in, so it's out there with pumps and motors. And valves. It's an industrial staple that is done everywhere. So cement, minerals, limestone, sands, these are things that you don't often buy them as a consumer, but it might surprise you to learn that concrete, for example, is the most used material on planet Earth after water. So the quantities of this stuff are gigantic, and most of it's been washed and dried at some point. Now, so drying is universal. The next thing I want you to soak in is drying is really energy intensive. So you know all the stuff that we use energy for. You heat your house, you drive your car, all that kind of thing. Industry has got a whole bunch of processes that are what's called hard to abate. And one of them is drying. Drying uses a lot of energy, and there's not many ways to get around it. Now, the reason why drying is difficult and energy intensive is that the way that we, humanity, dry things is we boil it, okay? Now, to give you an idea how much energy that uses, if you think about boiling a kettle at home, you fill it up, throw the switch, the water's at room temperature, and probably 2 minutes later, it's reached 100 degrees, okay? If you were to leave that kettle boiling, it might take half an hour to boil that dry, okay? Kettle's still working at the same level of energy input as it boils off the water as it was when it heated up, okay? But what took 2 minutes to boil might take half an hour to boil dry. So taking a liquid that's at 100 centigrade and pushing it into being a gas takes a lot of energy. So that's what's involved when we dry things by boiling them. Okay, so that's thermal drying. Like I said, it's very simple. We've been doing it forever. It works just fine, and holy moly, it's expensive. We do it lots of different ways. So, like I said, it's an industrial staple, and there are lots of ways of doing it because there are lots of different use cases and so on. So one of the most common is rotary drum. It's like a great big sort of tumble dryer. Fluidized bed is where you dry things on a kind of an air bed of air jets. Flash dryers is used in the chemical and process industry. Spray dryers the same. The point is there's lots of ways, but they all rely on the same energy equation. So we've been drying things 101 different ways, but it all boils down to boiling the water. Okay, so I've taken you through this a bit. You boil the water. You take it through the latent heat of vaporization. That's very energy hungry, but it works. So that can mean typically something like 200 kilowatt hours per ton to dry things like sand or cement and so on. And most of that, go back to my kettle analogy, is taking water you've heated up to boiling point and turning it into a gas. If you didn't have to do that, if you could avoid boiling the kettle dry, you'd have a lot of energy budget free to do other things with. And that's what we've done. So this is a cute but not particularly illustrative picture of how our stuff works. So basically, if you think of thermal drying as being like a tumble dryer, think of our stuff as being like a Dyson hand dryer. So we use what are called air knives, which is a very high-speed air jet over a surface to drive the moisture off. So we are doing for sands and all those industrial materials basically what a Dyson hand dryer is doing for your hands. And that's why it doesn't use much energy. So we can typically cut about 3/4 off the energy bill. Now, what we do, instead of having to boil it, we drop it into an airflow. We put it through a sequence of air knives. So you start with wet material and dry air. And by the end of our process, you have dry material and moist air. Now, what I mean by that is we keep that air just warm enough that it doesn't recondense. So you keep it above what engineers would call the dew point, so that moisture is then held in the air and it doesn't recondense onto the base material. So if you look at this chart here, you can see that this is an exponential graph. If you can keep your air above about 80 centigrade, you can carry a lot of moisture in it. Whereas if you drop it down to room temperature, it won't carry much. This is, when I say the dew point, you've seen dew in the mornings. This is exactly what's happening when you get dew on your lawn, is that the air is cooling, it can't carry as much moisture, and it drops that moisture out onto the grass. So that's what dew is. So you may well know this, I'm just probably covering old ground. But we use this principle. So we keep the air only warm enough to stop it recondensing. What we don't have to do is get it up to the point where we boil everything. So the commercial case is basically we save a lot of energy. Energy is expensive. More than just being expensive, I think we're moving into a world where energy is difficult. It's volatile. You can't always be sure that you're going to be able to source it when and where you want, in the quantities you want, at a predictable price, and so on. So decoupling from high volume energy supplies is just a sleep well at night thing for a business to do. And the reason we're all here today is that everything is tightening around energy and emissions. You know, it varies place by place. It may not be happening as fast in some as others, but the direction is only going one way. Now, I live in North America. Even there, where the cost of energy is much lower than here, you go to meetings and everybody understands that this is only moving one way. Even in countries that are energy independent, where energy has historically been cheap, even in those places, nobody is in any doubt about which way this is going as a kind of macro trend. So if we're using less of it, it's cheaper, splendid, but it's also greater independence. You've just decoupled your business from volatile, uncontrollable, difficult factors that could either stop your operation in its tracks or push it into a loss-making state. That gives you greater pricing power in the market. So this is our machine. I'll try and talk you through this briefly. So we drop the material into an airflow through a thing called a rotary valve. So we basically fire the material down this pipe. So the material goes whooshing down this pipe. These blue chambers here are banks of air knives. So as the material is going down that pipe, carried in a transport airflow, in those blue chambers, it meets a bank of air knives, which are high-velocity counter airflows. So those shear the moisture off the surface of the particles. So you start at the left end here with wet material and dry air, and by the time you've got here, you've now got a dry material carried in an airflow that is moister than when it began, but above the dew point. So that moisture is not going to recondense onto the material. At the end of that process, you send it into a cyclone. So now, second thanks to Mr. Dyson, you know the hand dryer. You may also have a Dyson vacuum cleaner in your house. If you do, that is a cyclone. So his principle is an industrial principle. He did what we did. He took an industrial process and, well, not quite what we did. He took an industrial process and reapplied it to the home. We're taking something he's used in a kind of retail environment and reapplying it industrially. But it's a cyclone. You can then separate a flow of particles from the air that carries them using a cyclone, which works the same way as a Dyson vacuum cleaner. And that's it. That is how our process works. This is our pilot plant. This is up in Adlington, near to Macclesfield in the northwest of England. So that's the first unit that we built at a kind of industrial scale. We've now built we've sold 2 major industrial units. One is currently being commissioned in Australia, where it's being used in a hydrogen, coal to hydrogen program. And the second unit is going in the UK later in this year, where it's being used to dry coal ash, which is used as a substitute in cement. So low energy, it's robust. These chambers here, because they're air knives, they don't have any moving parts. So this is by its nature quite a simple and robust system. It's complex to set up the fluid dynamics so that it works, but having done that, there are no moving parts. So that's kind of a CAD rendition of the process chart that I showed you earlier on. So this here is where the materials are entering the dryer. This is the line down which it flows. These blue pieces are the blue pieces from the chart where the air knives are. And these are the cyclones. Now, these gray shadows here are 40-foot shipping container dimensions. So it's about the size of two conventional shipping containers. It's demountable as well, so you can use it someplace, and then when you're done, put it on a truck and take it somewhere else. In a bit more detail, that's the detail CAD of the drying cartridges, so you can sort of see what they look like. And that's the unit in the metal being built. So these are the drying cartridges. Inside here are the air knives. That's looking end on. If you were to look down the pipe of this, you'd be looking through an empty pipe. There is absolutely nothing to see. So it's just a straight pipe, and the air is coming in, from the side at very high speed, and that's how it's removing the material. There it is on a truck. That's going on a truck in England, bound for Australia, where it has now arrived. But that you can see, that's the frame to a shipping container dimension that it's built to. Oh, okay, thank you. Yeah, this is the wrap-up slide. So we have an pilot plant facility in Atkinson in the northwest of England. You can send us your material. We can trial it and give you a rundown on the energy balance of it, how it processed, and so forth. So, and that is it. So I'm the North American contact for the business. Philip Jarvis, who you deserve to have, will be here tomorrow. Runs the UK operation. So, and that is it.
Thank you so much. Does anyone have any questions? So I can bring the microphone over to you.
Yeah.
Is the technology suitable, or do you think it would be suitable for things like food and pharmaceutical products, which start off life as a powder and then gets turned into, say, a tablet or something of that nature? Do you think that you could use that for this?
So the question is, would this be suitable for things like food and pharmaceutical products that start off as a powder and are turned into tablets? Is that right? Okay. So the answer to that is yes and no, and here are the reasons. It's very suitable because this is low temperature. So partly because we're not boiling it, so most thermal dryers dry at 300 or 400 centigrade. And if particularly you might have a pharmaceutical molecule that does not like to get that hot. So the yes part of the answer is it's very suitable because it's low temperature. The maybe not part of the answer is that we dry the surface moisture because of the air knife principle. And if you have moisture deep down inside fissures in the material, we will probably not be able to remove that. And for some food and pharma applications, that matters a lot, and others it doesn't matter at all. So, for example, I was speaking to somebody a little while ago who was trying to dry the outside of oat husks in order to remove the husk, but he didn't want to dehydrate the oats inside. So the answer to your question is yes, with some caveats.
Thank you. Any other questions from anyone? Great.
Hi, just looking at the pictures of the dryer that you've got there, is it sort of like a modular system where you can modify the size of it based on what sort of dry substance you need to get to?
So the question is it a modular system that you can scale up and down? So is that right? So the answer is yes, exactly so. It is a modular system, and it's an insightful question to ask because most systems you size them for whatever you're doing, particularly rotary drums. You size them at one size, and it is what it is. This one you would add more units, or subtract depending on. So that has pros and cons depending, but you are exactly right. It is a modular system.